Hello everybody. So in this video we continue with chapter 16, Integral Calculus 2, specifically with section 16.3, Numerical Solutions, Euler's Method. And first we're going to start with slope fields. So often the primary objective when solving a first-order differential equation is to find an explicit solution. So we found explicit solutions and also implicit solutions in the previous two sections of this chapter. However, many differential equations used in mathematical models cannot be solved by means of an analytical method. That means with algebra. For such equations, we must resort to graphical and/or numerical methods, which means approximations. These can be carried out by hand or by technology and provide us with a rough qualitative information about the graph of a solution to a differential equation. A first-order differential equation in the form dy dx equals f of xy specifies the slope of the solution curve y equals f of x at each point in the xy plane where f is defined. So let's recall that a first-order differential equation means that it has a first derivative as the highest derivative. And basically what they're saying here is that if you have, for instance, a slope field for this equation, dy dx equals x minus y, each one of these lines represents the slope of the original function, of the antiderivative, at each one of these points, right? Because this represents the derivative. So look at, for example, point 1, comma 1 is a flat line. That's because if we plug in 1 here, 1 for x and 1 for y, we get 0. So the slope is 0. If you look at 2 comma 1, that's going to be 2 minus 1. So we have a slope of 1. If you take a look at 1 comma 3, we get negative 2 as a slope. Notice that we get negative 3 as a slope for 1 comma 4, negative 4 as a slope for 1 comma 5. And so forth. So this represents the slopes at any given point. So this is why it's called a slope field. A plot of these line segments showing the slope or direction of the solution curve is called a slope field, or also known as a direction field, for the first order differential equation. As a rule, the segments are drawn at representative points evenly spaced in both directions. So we can see that these points are all evenly spaced. So if you take a look at figure 16.9, you can see that the solutions to a differential equation can be sketched using the slope field. So you can see here 3 different curves that were sketched using the slopes obtained from the differential equation. As you can imagine, it can be quite tedious to draw a slope field by hand. In practice, slope fields are easily generated by suitable graphing technology. As I said before, solutions to a differential equation can be sketched by drawing curves that are at each point tangent to the line segment at that point. Thus, a family of solution curves can be produced. To use a slope field to sketch a particular solution, all we need to know is one point, an initial condition, that the solution curve passes through. In this course, luckily, you will not be asked to draw slope fields, but they are mentioned here as they help you understand the method used in the following procedure, which is Euler's method. In cases where we are interested in finding a particular solution, the numerous line segments of a slope field could be distracting. Euler's method, developed below, enables us to approximate a single solution curve. The method is based almost entirely on the idea of a slope field. So we consider the initial value problem, dy dx equals x plus y, and we have the initial value, y of 2 equals 0. So figure 16.10 shows the slope field for the differential equation dy dx equals x plus y. So we see that right here. An approximation to the particular solution can be sketched by drawing a smooth curve at the point 2, 0 that follows the slopes in the field. So notice that this would be the point 2, 0, and the curve follows the slopes in the field. Let y of x represent the solution curve. So this is y of x. To approximate a value of y for a specific value of x, for example, when x equals 3, so when x equals 3, this would be the value of y. We can make an educated guess from the sketch of y made with the aid of the slope field. But if we want a more accurate approximation, we need to use a more refined method. The simplest numerical method is called Euler's method, after the prolific 18th century mathematician who first devised this computational method to help him calculate the orbit of the moon. Euler's method uses the basic idea behind the construction of slope fields to find numerical approximations to solutions of differential equations. Let's illustrate the method with the initial value problem that we have just been considering. We know from the differential equation that the slope of the solution curve is 2 at the point 2, 0, because if we plug in 2 for x and 0 for y, we're going to get 2. Hence, the tangent to the solution curve at 2, 0 has the equation y minus 0 equals 2 times x minus 2. So this is just the point slope formula. Recall that y minus y1 is equal to m times x minus x1. So it's just plugging in the points and the slope, right? So we get y equals 2x minus 4. We can use this tangent line as a rough approximation to the solution curve. See figure 16.11. So notice that this here is the tangent line at 2, 0. This approximation clearly becomes less accurate as we move away from the point of tangency. So notice that here it's very inaccurate, and here it's also very inaccurate. Euler's method improves this approximation by moving a short horizontal distance. This is called step size h along this tangent line and then changing direction according to the slope field. In this way, we build an approximation to the curve by attaching little line segments together, each having the slope of the solution curve at its starting point. In general, after being presented with an initial value problem, dy dx equals f of xy, y of x sub 0 is equal to y sub 0. We choose a step size h, starting at the point x sub 0, y sub 0 for the interval. Notice that the interval is going to have x between x sub 0 and x sub 0 plus h. We approximate the solution curve with the tangent line, that is, the line with slope f of x sub 0, y sub 0. This takes us as far as the point x1, y1, whose coordinates are calculated as follows. So notice that x1 is equal to x sub 0 plus h, which we can see here. And then here it says y2, but this should read y1 is equal to y sub 0 plus h times f of x sub 0, y sub 0. So notice that f of x sub 0, y sub 0 is the slope of this line, and that the new point x1, y1 is found by adding the step h to x and by multiplying h times the slope, the original slope, and adding that to y sub 0. Repeating this process, we get an approximation to the solution curve consisting of line segments joining the points x sub 0, y sub 0, x sub 1, y sub 1, x sub 2, y sub 2, etc. Each computed value, y sub n, is an estimate of the corresponding true solution, y, at x equals x sub n. The accuracy of the estimates depends on the choice of the step size h and the overall number of steps or iterations. Obviously, that decreasing the step size while increasing the number of steps or iterations leads to increasingly more accurate estimates for the solution values. So this is the real curve, the solution curve right here, and this would be Euler's approximation. Notice that the dots are the points that you find using his method. Okay, so now let's take a look at example 16.26, and it says, For the differential equation dy dx equals x plus y, such that y of 2 equals 0, use Euler's method with a step value of 0.2 to find an approximate value of y when x equals 3, giving your answer to 2 decimal places. Okay, so notice here that the step h is equal to 0.2, and we also have that x sub 0 is equal to 2, whereas y sub 0 is equal to 0. And then each iteration is going to be in the form for x, so x1 is going to equal x sub 0 plus h, and then we have that y1 is going to equal y sub 0 plus h times f of x sub 0, y sub 0. So x1 is going to be 2 plus 0.2, which is 2.2, and then y1 is going to equal 0 plus 0.2 times 2 plus 0. That's using this here, right? The differential equation. And this equals 0.4. And then we continue this in the same way until we reach 3 for x. So notice that y is approximately 3.46. That's rounded to 2 decimal places when x equals 3. Now this method is very tedious if we have to do it by hand. Luckily, we can use the graphing display calculator. So that's what we're going to do next. So what we need to do first of all is go to mode and change the mode functions to sequences. Now this is obviously a recursive sequence. So next we press y equals, and notice that instead of getting a space to write equations, we have this space to write sequences, a recursive sequence in this case. We saw this during sequences about a year ago. Okay, in any case, what says n minimum, n is just going to be your counting. So n minimum will be 0 because we have x sub 0 and y sub 0. U of n is going to be the way to get x, right? So to get the next x value, we would do the previous value plus h, but now we have to write the same thing in terms of u. So we'd say u of n is equal to u, and you find u above the 7, so u, and in the parenthesis, n, which is right over here where the variables are, n minus 1, that means the previous term, plus h, which in this case is 0.2. 0.2. And then where it says u of n minimum, so u of 0, in other words, x sub 0 is the initial value, which is 2 for x, right? Okay, now we go down to v of n, and that is going to be the recursive formula for y. So we would type second v, which is above the 8, v of n minus 1, or the previous value for y, right? V of n minus 1 plus 0.2 times the slope, which would be found by plugging into the differential equation the initial values, for example, of 2 and 0. But in general, it would be u of the previous term, n minus 1, plus the previous y term. So v of n minus 1. And we have to close this parenthesis and the other parenthesis. Next, we have to put the minimum value for y, which is 0. And now we go to second, and above the graph button, which says table, we click on that. And notice that we get a table. And notice that for the fifth iteration, we have x equals 3. In this case, u of n equals 3, right? And notice that the approximation is the same, 3.465. The advantage of the table is that this keeps going on and on and on and on. So you can find the approximation to y with any value of x, considering the step to be 0.2. Now imagine you can be much more accurate if you use an h that is lower, right, like 0.001. So this is how you do it with the GDC. So now we're going to take a look at example 16.27, which will be the last one on this video. So it says, given that dy dx is equal to x plus 1 over xy plus 2, and y equals 1 when x equals 0, use Euler's method with step size h equals 0.25 to approximate the value of y when x is equal to 1. Give the approximation to 3 significant figures. Okay, so for this, we're not going to do it by hand. I'm going to use the GDC. So again, in mode, make sure that instead of functions, you have it set up for sequences. Then click on y equals, and normally for these cases, the n minimum is going to be 0. So u of n is going to be u of n minus 1. So we type second 7 parenthesis n minus 1 plus the step, which in this case is 0.25. 0.25. And then the minimum is the first value of x, which is 0. Now we have to type v of n. We have to be careful here with parentheses. So it's going to be the previous v, or the previous y. So we go second 8, v of n minus 1 plus h, which is 0.25, 0.25 times, that's the first parenthesis, and then here we have to write x plus 1. So x plus 1 is the previous value for u. So we would write u, and I'm going to use a parenthesis here, u of n minus 1, that's the previous value of x, plus 1. We close the parenthesis for what's on the numerator, divided by parenthesis, and this is x times y. So the previous value for x, which again is u n minus 1, times y. So times v of n minus 1 plus 2 plus 2. So we close the parenthesis for the denominator, and we close the parenthesis for the full expression. And then let's not forget the minimum for y, which in this case is 1. And then we hit enter, and second table. And notice that on the left-hand side we have the iterations, and the x value 1 is right here. And it says round to 3 significant figures, so y would be 1.55.